The kinetic molecular theory looks into more detail at things like the distribution of speeds in a gas sample. So here's a graph that shows how many molecules of the gas have a certain speed. The black line represents when the temperature is 200 Kelvin, and the red line is when the temperature is increased to 1000 Kelvin. So you can see when the temperature is lower, we get a sharper curve, a narrower distribution that broadens out when the temperature increases. So we get a bigger distribution at a higher temperature, and the most probable speed, the one where the most molecules are found, shifts to a higher speed, which makes sense. As we increase the temperature, more molecules are going to be moving at a faster speed. We can calculate the average kinetic energy, which works out to be 3/2 times the gas constant R times the temperature T. This gives us the average kinetic energy of 1 mole of a gas sample. And the interesting thing about this is everything is a constant if we're talking about one particular temperature. So, for example, if we compared argon and krypton at the same temperature, because they're at the same temperature, those two gases will have the same average kinetic energy. And kinetic energy is given by this formula, 1/2 times the mass times the velocity squared. So even though the average is the same, we know that argon has a much lower molecular mass, molar mass, 39.95 grams per mole compared to krypton. So when the mass gets smaller, the velocity has to increase in order to get the same kinetic energy. So what this is telling us is something that we already know. If you have a sample of relatively light molecules, they're going to be moving with an average velocity that's higher than if you have heavier gas particles. And you can see this in an effusion experiment. Effusion is very similar to diffusion. Diffusion is when a gas spreads into another gas. If you open up a bottle of perfume, it diffuses into the air in the room. In this case, effusion is the gas particles moving into a vacuum. So we have the sample of the gas on the left, a small opening on the right that's connected to a vacuum. So as the gas particles move randomly throughout the container and they're colliding with each other, eventually a gas particle will find that small opening and enter the vacuum side. How fast the gas effuses is given by this formula. We've gotten rid of the constants because we're setting up a ratio where the constants drop out. So the nice thing about this formula is, just like we were saying before, a heavier gas on average travels slower. So if the gas particles are heavy particles, they're going to effuse at a very slow rate. If you have tiny particles with a very light mass at the same temperature, they're going to find that opening quicker because they're moving around the container faster. So we can do a problem where we compare helium to neon. It doesn't matter which one we put on the top and which one we put on the bottom, but we know that helium is going to be the faster rate of effusion because it's the lighter gas. So I'm going to put the bigger part of the fraction on the top, and the rate of neon will be on the bottom, and this equals the square root of the molar mass. And notice the gas neon, we have to put the molar mass of neon on the top, and we have to have the molar mass of helium on the bottom. From the periodic table, the molar mass of neon is 20.18 grams per mole. Neon, or helium rather, 4 grams per mole. So the grams per mole cancels. 20 divided by 4 is about 5. Take the square root and you get 2.25. So what this is saying, the rate of helium versus the rate of neon, it's equal to 2.25 or 2.25 to 1. In other words, the helium effuses 2.2 times faster than neon, which is what we knew. The lighter gas has to effuse at a faster rate.